Section: Introduction. In this section, we will discuss Transformer Large Language Models, LLMs, and their challenges. Transformer LLMs are advanced in generative and conversational AI. However, their efficiency is limited due to the quadratic complexity of attention layers. During generation, transformers store past tokens, keys, and values in memory to avoid recomputing them multiple times. This key value, KV, cache grows with the sequence length and batch size, making generation with transformers memory intensive, especially for long context generation or serving many user queries. To address this memory efficiency issue, grouped query attention, GQA, is commonly used, which reduces the number of key and value heads compared to query heads through parameter sharing. Other methods like token merging or pruning aim to reduce the number of tokens in memory but often lead to decreased performance in downstream tasks. Hardware, EO-aware, and sub-quadratic algorithms for attention do not solve the memory load problem of the KV cache. Our goal is to compress the KV cache of LLMs without losing performance. We introduce dynamic memory compression, DMC, which decides whether to add current key and value representations to the cache or perform a weighted average with the top item in the cache at each time step. DMC ensures memory grows sublinearly, balancing between vanilla transformers and state space language models where memory is constant. We apply DMC to existing LLMs like Llama 27B, 13B, and 70B by incorporating it into a small portion of the original pre-training data without adding extra parameters. Evaluations on various tasks show that DMC maintains performance similar to the original LLM, unlike GQA, which degrades performance significantly. Combining DMC with GQA leads to compounded compression rates. For instance, DMC2x with GQA8x achieves a total compression of 16x for Llama 270B. DMC enhances generation efficiency practically, increasing inference throughput by 340% to 370% for Llama 27B and 13B on NVIDIA H100 or A100 GPUs without sacrificing performance. It allows larger batches and longer sequences within a given memory limit. Additionally, DMC reveals insights into LLM internal structure and introduces a new method for compressing key value representations based on soft routing, improving efficiency without performance loss. By retrofitting vanilla pre-trained models with our method, we demonstrate improved performance compared to state-of-the-art methods like GQA, with efficient routing strategies and weight extraction from token representations. Section Summary. In this section, we introduce Transformer Large Language Models, LLMs, as cutting-edge in generative AI but limited by inefficiency due to the quadratic complexity of attention layers. To address this, we propose dynamic memory compression, DMC, to compress the key value cache of LLMs, reducing memory load while maintaining performance. Through experiments on downstream tasks, we demonstrate that DMC outperforms existing methods like grouped query attention, GQA, in efficiency and performance, showcasing its potential for enhancing large-scale language model applications. Section: KV caching during inference. In this section, we discuss KV caching during inference in transformer decoders. When generating sequences in a transformer decoder, we predict each new token based on the tokens generated before it. To avoid repeating calculations, we commonly store the keys and values of previously computed tokens in the KV cache. At each time step I, we only compute the keys and values for the current token x_i, while retrieving those for x_i from the cache. This process is not needed for queries since only the query for the current token x_i is required at each inference time step. However, the KV cache grows linearly with each new token, leading to increased memory usage and latency, especially for long input sequences. This problem becomes more challenging when handling multiple requests simultaneously, as each inference process needs its own KV cache, putting a strain on the system's resources. We introduce dynamic memory compression, DMC, as a method to address this issue. Inference with large language models, LLMs, is often limited by memory rather than computation, meaning that latency increases with the size of the KV cache. By reducing the size of the KV cache, we can decrease the latency of generating sequences and improve throughput by saving GPU memory, allowing for larger batch sizes or sequence lengths. DMC is a simple and cost-effective method for compressing the KV cache during inference. During inference with DMC, we update the KV cache differently compared to a standard transformer. We predict a decision variable alpha_t and an importance variable omega_t at each time step t. Based on alpha_t, we decide whether to append the representations k_t and v_t to the cache or accumulate them with the last element. This decision is made using predicted importance scores and a weighted average calculation. The alpha variable segments the input sequence, determining whether to continue the current segment or start a new one. As a result, the length of the cache with DMC is less than or equal to t, unlike in vanilla transformers where it is always equal to t. The ratio between the uncompressed cache length t and the compressed length L is referred to as the compression ratio, CR. Training LLMs with DMC involves gradually increasing the compression rate towards a target by continuing pre-training with a small amount of data. We face challenges such as defining cache updating operations for intermediate states and simulating DMC behavior during training to avoid training inference discrepancies. These challenges are addressed through end-to-end learning, continuous relaxation of decision variables, and explicit storage of all intermediate states during training. Section Summary. In this section, we introduce dynamic memory compression, DMC, as a method to reduce the size of the KV cache during inference in transformer decoders. By dynamically compressing the cache, we aim to lower latency in autoregressive generation and increase throughput by saving GPU memory, allowing for larger batch sizes or sequence lengths. DMC involves predicting decision and importance variables to determine whether to append or accumulate key value representations in the cache, effectively reducing the cache length compared to traditional transformers, leading to improved efficiency during inference. Section: Gradient estimation for discrete decisions. In this section, we tackle the challenge of estimating gradients for discrete decisions in our model. When deciding whether to accumulate or append during inference, we face a discrete choice. However, rounding the sigmoid of a value to the nearest integer for training causes issues with differentiability. To address this, we use stochastic reparametrization during training, introducing a temperature parameter tau and a constant c to adjust the decision variable alpha. This ensures that our model initially behaves like a standard transformer with no compression. As we relax our discrete decisions, we introduce a mechanism to update the KV cache for continuous alpha values. We define partially accumulated states for alpha between 0 and 1. This approach generalizes the update process for the KV cache. During training, we face a mismatch between the parallel processing of tokens and the sequential nature of key and value computations. To address this, we keep track of all intermediate KV cache items to simulate the inference time evolution accurately. We modify the attention scores using a mask based on the sequence of alpha values to align training and evaluation processes. Our training objective focuses on compressing the KV cache to a specific compression rate, CR, by adjusting the predicted alpha values. Instead of matching the desired rate for each decision, we calculate a global loss based on the expected sum of KV tokens under the desired CR. This loss is combined with the language modeling loss to form the final training objective. We gradually increase the desired compression rate during training and allow for flexibility in stopping this ramp-up process. This approach enables us to train models with varying compression rates within a single run without decaying hyperparameters. DMC enables each head to learn a unique compression scheme, leading to KV cache sequences of variable lengths across heads. We implement a custom attention mechanism in PyTorch that accommodates variable length caches without the need for padding. This design choice optimizes memory usage, allowing for increased batch sizes and improved throughput during inference. Additionally, we explore a constrained variant, DMCC, that enforces similar compression rates across heads in a layer, reducing the need for padding but potentially impacting model quality. Section Summary. In this section, we address the challenge of gradient estimation for discrete decisions in our model. We introduce stochastic reparametrization during training to handle non-differentiable operations and ensure the model behaves like a vanilla transformer initially. Additionally, we discuss the implementation of variable length cache without padding, allowing each head to learn a custom compression and improving efficiency during inference by reducing memory footprint. Section: Window Grouping Approximation. In this section, we tackle the challenge of approximating window grouping. When training DMC models, calculating partial accumulations for a sequence of tokens can be time-consuming, requiring many sequential steps. To speed up training, we calculate these partial accumulations independently at each time step over a short window of the last elements up to that time. By doing this, we reduce the computation span significantly, making it more efficient. In our experiments, we explore ways to enhance the efficiency of a state-of-the-art large language model, LLM, Llama 2, across different sizes, 7B, 13B, and 70B. We compare the performance of DMC with the original model and use grouped query attention, GQA, as a key baseline strategy for KV cache efficiency. To incorporate GQA into the original Llama 2, we follow a standard checkpoint conversion method where key and value projection matrices are split by head and then merged for heads in the same group. This process maintains a fixed compression ratio during training. For DMC, we repurpose dimensions from key and query representations to predict segmentation decisions and importance scores, avoiding the introduction of new parameters. We pre-train the model to ignore certain dimensions in attention calculations to prevent a significant increase in language modeling loss. We adhere to specific training hyperparameters, utilizing the Atom W optimizer with defined parameters, weight decay, and gradient clipping. The batch size, context length, learning rate, window size, and Gumbel sigmoid temperature are set accordingly for efficient training. The training schedule for DMC depends on the targeted KV cache compression ratio, with more data required for a higher compression ratio. We gradually increase the compression ratio during training and implement a final solidifying phase to stabilize the model with a fixed compression ratio. This phase involves additional up-training, maintaining compression ratio, and adjusting the learning rate schedule. Through various ablations, we ensure that any increase in perplexity during training does not hinder the model's performance on downstream tasks. Section Summary. In this section, we introduce a window grouping approximation to speed up training for DMC models by calculating partial accumulations over short windows of the last W elements, reducing computation complexity to O(W). We evaluate retrofitting strategies for a large language model, LLM, into a more efficient model, comparing performance with grouped query attention, GQA, as a baseline. Additionally, we adapt the original Llama 2 model with GQA by splitting key and value projection matrices by head and merging submatrices, while repurposing dimensions in DMC to predict segmentation decisions and importance scores without introducing new parameters. Section: Evaluation. In this section, we evaluate models on various tasks such as factuality, Python code generation, and common sense reasoning using different datasets like PIQA, BoolQ, ArcC, ArcE, HelloSwag, and Wino Grande. We present the performance results for different tasks and model scales. We compare the original LLM with efficient variants like DMC and GQA. When comparing DMC with the original LLM, we find that DMC improves performance in tasks like factuality and common sense reasoning at twice the capacity for model sizes 7B and 13B. It also performs well in human eval for all model scales. DMC shows consistent performance across different tasks and model scales, even at 4 times the capacity. This suggests that DMC is a reliable option for improving inference efficiency. Furthermore, when comparing DMC with GQA at equivalent capacities, DMC outperforms GQA in both model sizes, 7B and 13B, and at different capacities. The gap between DMC and GQA widens as the capacity increases, especially in tasks like factuality. Overall, DMC proves to be a better choice for enhancing LLM efficiency during inference. We also explore the combination of DMC and GQA by retrofitting a model pre-trained with GQA with DMC. The results show that combining DMC and GQA does not affect performance, indicating that they can be used together effectively. Additionally, we compare DMC with its constrained variant, DMCC, and find that DMCC has some performance degradation in certain configurations compared to DMC. DMC, on the other hand, maintains or improves performance compared to GQA. Therefore, standard DMC is preferred due to its ability to retain original LLM performance while enhancing memory efficiency. To understand the sample efficiency of DMC and GQA, we analyze their performance on different tasks across retrofitting steps. We observe that DMC achieves better performance after fine-tuning compared to GQA, even with fewer fine-tuning steps. This highlights the importance of the fine-tuning phase in DMC, as it helps recover a significant amount of the original performance, especially at higher capacities. Section Summary. In this section, we evaluate various models on different downstream tasks such as MMLU, human eval, and common sense reasoning datasets like PIQA, BoolQ, ARC-C, ARC-E, HelloSwag, and Wino Grande. We compare the performance of the original LLM with efficient variants like DMC and GQA, noting that DMC outperforms GQA in MMLU and carbon monosulfide QA across different model scales, making it a suitable replacement for KV caching to enhance inference efficiency. Additionally, we find that combining DMC with GQA can yield compounded benefits without sacrificing performance, and DMC is preferred over its constrained variant DMCC due to its ability to retain original LLM performance while improving memory efficiency. Section: Throughput and Latency Measurements. In this section, we present the results of our experiments on throughput and latency measurements. We tested the efficiency of DMC within the NVIDIA Megatron LM framework by running measurements on different GPU setups using English text models. By compressing the KV cache with DMC, we were able to increase batch sizes and improve throughput significantly. The efficiency gains observed in practice were close to the theoretical limit, showing a substantial increase in tokens processed per second compared to the original LLM. When comparing the latency of the original LLM with DMC, we found that increasing the batch size led to linear scaling of inference time with context size due to reading the KV cache from high-bandwidth memory. However, maintaining the same batch size for DMC as the original LLM reduced the memory footprint of the KV cache and improved latency for longer contexts. Our measurements indicate that DMC enhances throughput and reduces latency in autoregressive generation with LLMs. We speculate that in the future, DMC could be used to expand the KV cache sublinearly, offering a middle ground between vanilla transformers and state space models in terms of memory usage. Additionally, we analyzed the compression rates learned by the model during training. We found that compressing deeper layers was the most common strategy across different model scales and compression rates. Interestingly, DMC achieved high compression rates for several heads in the early layers, which could impact decision-making during token generation. Our work builds upon previous research on efficient inference in transformer models, focusing on reducing KV cache size. Compared to existing methods, DMC dynamically adapts the compression schema based on the input sequence, leading to superior results. By merging tokens instead of dropping them, DMC preserves information more effectively. Furthermore, DMC integrates compression into the learning objective in an end-to-end manner, enhancing language generation synergistically. Overall, our findings demonstrate the effectiveness of DMC in improving efficiency and latency in autoregressive generation tasks with LLMs.